Welcome to my workshop. In this video, I'm going to introduce you to this CNC router that I designed and built myself. It combines a welded steel frame, commercial linear motion hardware, stepper motors, and a computer-based control system. I'll show how the machine works and then use it to make a real project. A CNC router is a computer-controlled cutting machine. The process starts in CAD or vector design software, where the part is drawn at its finished size. The software then turns that design into toolpaths, the routes the cutter will follow. Those toolpaths are exported as G-code, a text-based set of machine instructions that tells the CNC router where to move, how fast to move, and when to cut. I use Mach 3 by Artsoft to actually control the CNC router. Mach 3 reads that G-code and sends motion commands to the machine. I built this machine to handle woodworking, plastics, PVC sheets, and similar materials. The design uses a moving table for the X-axis and a fixed steel structure for the Y-axis. That arrangement made the machine easier for me to build while giving the router a very rigid support. The main frame is welded from 2-inch square steel tubing. The machine has approximately 45 inches of X travel, 23 inches of Y travel, and 7 inches of Z travel. The overall machine is about 72 inches long, 36 inches wide, and 36 inches high, mounted on a 3-foot tall stand. The X-axis moves the work table beneath the router. The Y-axis is mounted on a fixed steel frame instead of a moving gantry. My main concern during the design was rigidity, and this configuration keeps the router support very stable. In this shot, you see the machine executing an auto home, where each axis moves to a precise starting position over the lower left corner of the work table. Before cutting, I use a touch plate and a Mach 3 macro to set the Z height as shown here. The system senses the moment the router bit touches the aluminum plate and zeroes the Z-axis based on the known thickness of the touch plate. I normally cut between about 15 and 60 inches per minute. The machine is capable of faster movement, but for most of my work I prefer approximately 35 inches per minute because it's predictable and easy on the tooling. Each axis rides on 20mm supported linear rails. Motion is produced by 16mm ball screws with 2 bearing blocks. The screws have a 5mm pitch and a double start thread, so the actual lead is 10mm per revolution of the ball screws. Ball screws give smooth motion with very little play, which is one reason the machine can return to the same position consistently. Because the frame was welded rather than precision machined, I mounted the rails and screw supports through slotted holes. That allowed me to align everything with shims and careful adjustment. In the previous scene, you saw the machine run its automatic homing sequence. In this close-up, you can see the Y-axis safety limit switch and the separate home or zero switch it uses to establish that reference position. The X, Y, and Z axes use 425-ounce-inch NEMA 23 stepper motors. Each motor is controlled by a DM542T stepper driver and coupled directly to its ball screw through a flexible shaft coupler. There are no belts or gearboxes in the drivetrain. The motors are set for 3,200 steps per revolution. Because the double start ball screws have a 10mm lead, the calculated setting is about 8,128 steps per inch. That number represents commanded motion resolution, not guaranteed machining accuracy. In actual use, I have measured repeatability of less than 5/10,000ths of an inch. The motor drivers, breakout board, Ethernet SmoothStepper, and power supplies are all mounted together in this control enclosure. The SmoothStepper receives commands from Mach 3 over Ethernet, and the breakout board distributes the step and direction signals to the individual axis drivers. A ball screw assembly consists of a screw and a nut with matching helical grooves. Steel balls roll between those grooves, providing the contact between the screw and the nut. As the screw rotates, the balls travel through the grooves and are redirected into a return channel inside the nut. They circulate back to the opposite end and re-enter the grooves in a continuous closed loop. This rolling contact reduces friction and converts the motor's rotation into smooth, precise linear movement of the machine axis. The Z-axis carries a Hitachi M12VC router in a rigid aluminum mounting assembly. I designed and built the Z-axis out of 1/2-inch aluminum plate. I built most of this by hand using a drill press. Later, I refined some pieces using my Grizzly CNC milling machine. Router speed is adjusted manually, and I normally run it at about 90% of full speed. Dust collection is especially important on a router this size. Depending on the material and depth of cut, the router can produce a lot of dust. I built the dust shoe myself and connected it to the shop's large vacuum system. It captures most of the chips and fine dust close to the cutter. The machine is controlled by a Dell laptop running Windows 11 and Mach 3. Vectric Aspire is used to create the G-code from the CAD drawing. Mach 3 sends motion data over Ethernet to the SmoothStepper, which generates the accurately timed step and direction pulses. The breakout board distributes those signals to the individual stepper drivers, and the drivers supply current to the motors. Mach 3 has been remarkably reliable, and I've used it for many years. For a demonstration of the machine in use, I'm going to make a carved wooden sign. I'll begin with a quick look at how I prepare the project in Aspire. After that, we'll move into the shop, load the file into Mach 3, and cut the sign. Here you can see the Aspire design view with the sign layout already loaded. Before creating the toolpath, I check the job setup. This defines the size and thickness of the material, the X and Y origin, and the Z0 position. Next, I switch to the toolpaths view and create a V-carve toolpath. This directs the cutter to carve the lettering and graphic details in the design. On the V-carve toolpath screen, I confirm that a 1/2 inch 60-degree V-bit is selected. Aspire then calculates how deeply the bit must travel to cut each part of the design. Once the toolpath is calculated, I use Aspire's preview function to simulate the machining operation and verify that the finished sign will look the way I intended. The final step is to save the toolpath, making sure the correct Mach 3 post-processor is selected. Aspire then converts the toolpath into the G-code Mach 3 will use to control the router. That completes the design and toolpath setup. I'll now transfer the G-code to the shop computer and prepare the machine for cutting. At the machine, I secure the wood to the moving table, install the V-bit, load the G-code into Mach 3, and set the workpiece 0. After checking the toolpath display and confirming that the cutter has adequate clearance, I start the router and begin the cut. The machine then follows the program paths, carving the lettering and graphic details. This is where the mechanical alignment, motor calibration, control electronics, and software all have to work together. I'm not using the dust collector for this cut to allow you to see the cutter head in action. Here is the sign immediately after machining. To add color, I apply acrylic paint over the carved lettering and graphics. I don't have to keep the paint completely off the surrounding surface because, after it dries, I sand the face of the sign. That removes the excess paint while leaving the color inside the carved areas. I then apply a pre-stain conditioner, wood stain, and a clear protective finish. Here is the completed sign after finishing. Projects like this are exactly why I built the machine. It gives me a useful working area, reliable positioning, and the flexibility to make one-off parts and crafts from a variety of materials. The machine has been dependable, and there is very little I would change in the basic design. Thanks for watching. To see more projects, technology, and how-to videos, like and subscribe.